You update on the project status of DKIST and show you some nice first light images and movies. That's basically the talk. But before I get there, I'd like to really acknowledge the people working on this project, and in this case in particular the scientists who are working on it. You see the list of co-Is. Phil Goody is here, and of course Michael has been a co-I for probably a decade or more, right? The instrument folks, people who are putting together instrumentation, are listed. Friedrich Würger, who is here, he's the BBI PI and also responsible for waveform correction, adaptive optics for the DKIST. Overall instrument scientist. Then Roberto Cassini, very dedicated. Alfred Devine, they're out there right now working on the WISP, finishing up the acceptance testing for the WISP. Hao-Sheng Lin, Sarah Yagli working on the DL-NIRSP. Jeff Kuhn and Andre Fellman, cryo-NIRSP. Oscar, Svetlana, and Wolfgang Schmidt are here for the VTF, and you will hear a presentation from Wolfgang on the VTF. Ali Tritschler is also here in the room. She's the operations scientist. So if we get to eventually submit and execute proposals, operate the facility on the summit, that's all her doing. A lot of work goes into that. Dave Harrington, Christian Beck, Tom Shad, polarimetry. And then in the UK, Mihalis, some of you may know him, is leading the UK consortium that has provided cameras, and you see the images from these cameras. And Mark Rast is chairing the science working group. And all these folks are putting in an immense amount of work. And we were kind of joking earlier, right, that Dirk Schmidt isn't here at the meeting. And I had to twist their arm pretty hard to come here to be at this meeting, because as they told me, I have work to do. And they do have a lot of work to do. And that's why they don't typically show up at workshops and meetings, but we shouldn't forget that those are the folks who are actually doing it all in the background. And of course, we have a large and really excellent engineering team working on this project. You have a picture here. It's actually not a very recent picture, but it's really some of the best engineers in the world that I had the pleasure working with. Great team, and they're putting all of this together. So with the first light, I think it's fair to say that we now have with DKIST, the largest solar telescope in the world. This was funded, construction and operations are funded by the NSF with contributions from partners, Germany and the UK. And here's a quick summary of major milestones. I start this list with a decadal review in 2000. You probably shouldn't forget the CLEAR effort by Jacques Beckers, which was before this in 95 through 2000. So if you put that all together, it's been 25 years for some of us on this project. The decadal review, of course, was a very important milestone. Being listed as a priority in that review is kind of a precondition to get something done. And Michael was on the decadal review committee in a very prominent role. He told me he actually wrote the report at the time. So that was an important milestone, an important hurdle to achieve. Not sufficient, but absolutely necessary to be listed in that review. Then, of course, proposals, site surveys, site selection, groundbreaking was when was this? End of 12. So we basically started construction at the beginning of 13. Let me just come to the bullets there in red to put that aside up front. So the end of construction is projected for end of June 2020. So the end of June this year is when we will be done with construction. That will be followed by a project closeout phase from July through September. There's a lot of work to be done in that phase. Besides the financial and administrative stuff that needs to be done, we also like to recoat the mirror right at the beginning of this phase to start with a fresh coating before we go into operations. There's a lot of technical work still to be done. Thermal systems, optical systems need to be optimized. So we'll use that phase for that, but also hope to take some data already. And that's data that we will take, very simple observations, basically to prime the pump for the data center, the calibration pipelines. And that data, as soon as it's calibrated, will go out to the public. So we will release that as soon as it's calibrated. Then we have this operations commissioning phase. That's a year-long period where we will accept proposals from the community, starting for a period, the first period of October 1. So soon, maybe May, we will start collecting proposals, ask for proposals, and then review those through a TAC process. And that will repeat, I think it's 3 times during that year, every 4 months, and ramp up during this phase the complexity of what we will offer to the community. We'll start with simple instrument configurations. I'll maybe give an example later, and then ramp up to the full complexity of all instruments available at the end of this period. That's the idea. That's the plan that we're working on, and soon you will see some announcements about the details. And then starting October 21, it's basically full operations, the normal proposal process. Found some pictures. Up there, upper left is groundbreaking, and you see, of course, Michael here on the left. Below that is a picture with Michael in front of the CUDA rotator, still at the factory in Rockford, near Chicago. The upper right, that's again groundbreaking. You know, Michael, as always, speaking softly, carrying a big stick, right? And then here a group picture. I think it was a team meeting or maybe a science working group meeting in Tucson. So again, Michael's been involved in this project right from the beginning and through the project up to now. And here's another nice one. He smiles. It's a nice picture. And then, of course, Michael, at least in the early years, was the PI for this instrument, the visible spectropolarimeter. Now it's taken over by Roberto Cassini as PI, but Michael was leading that in the early phases. I don't think I have to say much about this slide. This is just a reminder of what we're building. 4-meter off-axis telescope with adaptive optics, 1600 actuator, adaptive optics, coronal capabilities, 5 facility class instruments. And just as a reminder, it's going to put out, these 5 instruments are going to put out a lot of data when they're all operating. 12 terabytes a day, up to 50 terabytes a day on a good day. And then over a year, we collect 3 petabytes of raw data that then gets calibrated into 3 petabytes of calibrated data. So it's a big data machine, and of course at the back end we need a data center that can handle that and distribute data to the community. Again, I don't have to talk much about this. Main objective scientifically is to accurately measure the 3D magnetic field structure using all these diagnostic tools. And coming back to what I said earlier, in this phase, July through September, what we may hope to do is take some observations with a combination of 6302, 8542, with the WISP, do some BBI observations that kind of going to show later pictures of, and maybe the cryoNIRSP, some initial on-sky observations if we get the instrument ready to that point in that phase. So that's kind of what you can expect, and we hope to be able to put out some data, 6302, 8542, once it's calibrated. So just maybe to show or to demonstrate how quickly things have been moving forward in the last few years. This is from 2 years ago. We didn't have a mirror in the system yet 2 years ago. Just had a dummy mass in the mount, trying to ring out the mount, the pointing, and that's just 2 years ago. 1 year ago, this is a picture from of the CUDA lab, the instrument lab, and as you can see, it was still pretty much a constructing site at that point. HEPA filters here in the ceiling were not installed yet, and still a lot of work to be done. First benches being moved in. That was just 1 year ago, almost to the day. Thermal systems have been a bit of a challenge throughout the project and continue to be. We have to cool optics, we have to cool the dome skin. All that cooling has to be provided through pipes, 7.5 miles of pipes running through the facility. There's a separate building, this utility building that you see here, that provides cooling, ice tanks. We make ice during the night and use that ice to cool during the day. So there's an immense amount of support facility that has to be put in place and is being put in place. And that's been a challenge and continues to be one. We'll be optimizing thermal control systems probably for a number of years to come. And then here, December, first solar light. That was early December, where we pointed the telescope at the sun for the first time. So you see, if I can use the mouse here, you see here the aperture, 4 meter, slightly more than 4 meter aperture, through which the light enters and then hits the primary. So here you see the primary illuminated with light, and then the light hits the prime focus heat stop, and Oscar talked about that earlier. That's why we have a Gregorian design, so we can put a heat stop there and reject most of that light out of the system before we hit the secondary, which is up here. And then the light is sent down to the CUDA lab from there on through some additional optics. You also see this bright spot here that hits the enclosure, the inside of the enclosure. That's because we ran into some trouble with the original heat stop. It was an absorptive heat stop, absorbs all that heat. Developed problems with flow rates, liquid flow rates. So we had to quickly, the team had to quickly scramble to build a backup, temporary backup heat stop that reflects the light out so we could continue with the work. They did that within a couple of months. I mean, imagine that. You run into a snag like this, and then within a couple of months they have a solution in place. But this is temporary, so we will, actually that's in process, build another heat stop reflecting the light out, but to an absorber plate that will absorb it. So that's in the works now, and we'll be there in June. So first light down to CUDA. Now, with all the HEPA filters in place, this is a clean room, thermally controlled clean room. You go in there only with the appropriate gear. So forget the Dunn setup, the Dunn solar telescope, where everybody walks in there, including visitors, all the time, right? This is a clean room for obvious reasons. What you see here is first light to the waveform correction, the adaptive optic system. And then here, barely visible on this bench is the VBI. visible broadband imager, the first light instrument. And then here, light on the adaptive mirror. This is the 1600 actuator adaptive mirror. And then shortly after, December 10, it was, right, we started to take the first images. Didn't know what to expect. Like, you never know what to expect, what problems you might run into, what you might see. And when we saw the first images come on the screen, it was quite exciting, right? Like Phil mentioned earlier, this, oh, wow. Right, the first time you turn on this complex machine with adaptive optics and instrumentation, thermal systems not quite up and running yet, nothing optimized, nothing really verified, and this is what we got. This kind of imaging, I mean, this is now speckle reconstructed, but you have to start with excellent raw images to get this kind of result out of a speckle reconstruction. And to get this right out of the box, it was just amazing for us to see that. So you have seen that image, of course, right? So the interesting part are these bright points, these magnetic bright points, and the substructure in these bright points that we are seeing now. This is 789 wavelengths, 789 nanometers. Here is a very short movie just to show you that we don't just have one image, but that the image quality is actually pretty consistent. I should mention from analysis of HAO telemetry, we estimate that the L0 was about maybe 7 centimeters, 6 to 7 centimeters. So that's not the excellent type seeing that we can expect from Haleakala. That's kind of the median seeing that we, per site survey, expect from Haleakala. So median type of conditions. Yeah, each one of them. And of course, Friedrich sitting back there did all these reconstructions. Another interesting feature there, I thought, I can point the mouse to it. Here, if you look at this granulation, this granule here, how this sharp edge, bright edge moves, how quickly it moves, that's about the sound speed of how quickly that moves, whatever that means. I mean, we haven't really thought about any science interpretation or anything like that. It's just haven't had the time to get into that at all. Just another example here, same image, but H alpha now, and I'm gonna hopefully blink between the two images. So at the same time, when we took this data, we were switching between H alpha off band, so in the wing of H alpha, and this 789 nanometers. And you see the fibril structure in H alpha. And those are tiny. Those fibrils are really tiny. Some at the diffraction limit or close to, some a little larger, but it's really tiny features. And of course related to the bright points, as you can see, as expected. That's not a surprise. That's a short movie. I hope it plays and keeps playing. Now that's titanium oxide, so 706 nanometers, but basically continuum, of course, when you just look at granulation, just the different wavelengths. And also here, I think there's a lot of interesting stuff to be inferred from just looking at these images and movies. Once, hopefully, we get to that point where we can think about science again. Looks like simulations, right? Doesn't it, Matthias? So finally, the data looks like simulations. So the data must be correct, right? This is the movie I think that you have seen that was released for public consumptions, that was out there for the press. And you may notice that it's very smooth, hardly any noise. This has been filtered spatially and temporally for, again, public consumption. You know, so we don't get distracted by image flicker and oscillations and stuff like that. But it does take away a little bit of the resolution. So I'm going to show now the equivalent movie without that filtering done. And you see a lot more dynamic, a lot more spatial structure actually in that image. And if you just maybe watch some of these features here, I find that very interesting, how these guys develop over what is just about 4 minutes here, right? So again, there's a lot to be learned, I think, already from these few images in movies. This is just, yeah. No, it's not large. And here is a bit more noisy, the Halpha movie. Again, these fibrils developing very quickly on time scales of just seconds, right? You just see them change over 3 seconds. And really small scale fibrils. Halpha, I think we still had, or still have, a little problem with scaled light. And we also have problems with camera noise that we're working on. So just to give you the message that we're not done yet, right? There's still a lot of work to be done before this is a facility that is in normal operations. And just for Michael, first time we're actually showing this image, even within NSO. So this is fresh off the press, just for you, the first image of a sunspot. There it is. This is not even off the BBI, this is off the waveform correction, the adaptive optics context viewer, never intended as a science camera. It's a really cheap camera that is built into the adaptive optics system. And what you see here is this is 530, sorry, it says 430, but it's 530 nanometers. So green continuum. And this is what you see. And again, can one zoom in here? I guess not. I wanted to zoom in, but I can't. So just looking at the first image of this sunspot, there's a lot of interesting stuff here. Dark holes down here in this area. I can point to it right here. And what this is just a trace across a couple filaments to show what kind of resolution we're achieving. It's hard to read, I'm afraid, but we're getting close to 0.03 arc seconds. That's close to the diffraction limit at this wavelength. Not all fibrils or fibrils are of that size, right? In fact, many of them are more like a tenth of an arc second. The scale here is actually the tick marks, the small tick marks are a tenth of an arc second. Maybe, but I mean, it's a different type of scattering, right? I mean, the distance from, you're scattering from the photosphere into the sunspot over what is about maybe 10, 20 arc seconds. And when we do coronal, it's much, much more out there, right? So, but yes, I mean, in principle, we will learn something from that. Don't know yet. I mean, we haven't really done any analysis of that. Well, as the Big Bear telescope, as the GST, it's a unobstructed aperture, right? So that's about as good as it gets, right? Yeah, just an area disk. Theoretically, right? But we really have to look at what we actually have. Well, so that's where we are with images. I think it's pretty impressive, again, right out of the box to get this kind of performance. And again, it's a testament to the engineering team and the science team that we have, who have been working this for a decade now and really doing the detailed work, engineering, to get to this point. So now, as I mentioned, the WISP team, Roberto and Alfred, are out there finishing the integration of the WISP. And you see Roberto here giving the thumbs up. They're getting close to having this instrument accepted. And then we still have to do science verification on sky with the instrument. The Cryonosp has arrived on the summit now. Here you see it on the truck leaving the IFA, but it is on the summit and it's being integrated as we speak. DL-NIRSP has completed lab acceptance, is close to that, and that will ship within probably, call it weeks, couple weeks maybe, to the summit. And then the VTF, we'll hear from Wolfgang. We hope to have that arrive on Maui maybe at the end of this year. So this is also part of the operations commissioning phase, integrating the VTF into the system and getting it tested out. So bottom line here is there's still a lot of work left to do. Schedules are very tight. The team's getting tired. We're all getting tired. So please be patient when you ask for, when can I come to observe? Right? It's not quite there yet. Sure. It's installed. How long did it take? 2 campaigns, 6 weeks. 2 campaigns of 6 weeks total. Yeah, you should. Yeah, let's take that offline so we get through the presentation here. So I'm sure you guys have all seen the press coverage of the first flight images. It's been a big surprise for many of us how much coverage we got. But that's a good thing. I think that's good not just for this project, but for solar physics in general, to have that kind of coverage. I'll just go through some examples. And of course, that effort was led by NSF, their EPO department, our EPO department, other folks. So it's been a big effort, almost like another project. So all over the world, scientific journals, newspapers, right, news outfits. It was CNN even, US Today, right above, yeah, right underneath Trump. That's where you don't want to be. PBS, nobody made the connection between the solar corona and the coronavirus. It's a good thing. Yeah. BBC, Guardian, so heck if I knew. Yeah, so in here, we even made it into late night shows, right? This is kind of funny, right? We know what the surface of the sun looks like. and some other stuff, I mean. And here, of course, is that one, right? The New York Times above the fold. Go ask some people, I don't know. It's just good stuff, Phil. It's just good stuff. So, and this I had to have explained to me because I'm a social media illiterate. 1.6 billion people apparently have seen this image. So that's big. So with all this good news, Michael got a birthday present, right? He got a birthday cake just, when was it, a couple of weeks ago? With a picture of Decust on it, very appropriately. because of all his time and effort that he spent on bringing this project to a fruitful conclusion. And those of us who know Michael also know that if needed, he can light a fire, right? Sometimes. But then also, once the fire has done its job, he can put it out just as quickly. So with that, I'll stop.